Good morning. We are moving on today into our last chapter, chapter 44, Astrophysics and Cosmology, and feel like it's appropriate that this is kind of the finale for the course because once we start looking into astrophysics, we're going to find that we can actually use a lot of the concepts. If you think back to looking at how gravity works, different concepts from thermodynamics, quantum mechanics gets included. So everything gets utilized in taking a look at astrophysics. Now this is kind of an interesting diagram or photo that they have placed at the beginning of the chapter. What this is it's the current distribution of microwave photons left over from what's often referred to as the Big Bang. So the whole universe was in a hot, dense state. So there was a high temperature, high density plasma, and we can actually figure that that occurred somewhere roughly 14 billion years ago. The entire universe was in that state. Now, since that time, there's a leftover distribution of microwave energy photons that fill the entire universe. And since that initial state was so uniform, it looks just like the distributions, the photon distributions we looked at in chapters 37. So when we looked at the Planck radiation distribution functions, this almost exactly matches that. You can see that there's just some slight variations in temperature, and those correspond to quantum fluctuations from the very earliest stages of what we understand as kind of the development of the cosmos. This is a close-up picture. So the one before was kind of a wraparound. So that one before was actually drawn in a way where you could take this and wrap it entirely around, and then you'd be looking from Earth out into space at different locations. Across the center would be kind of an equator, kind of an equator of the photo that's being taken, and then poles at the top and bottom. This is kind of what the universe looks like now. So now when we look out into space, what we see are just galaxies and galaxies and more galaxies. And those galaxies are collections of hundreds of billions of stars. So this is an example of a set of photos taken by the Hubble Space Telescope, the Hubble Deep Field photos that were taken quite a few years back now. And you can see some of these galaxies are closer, so you can see more detail in them. But what you can also see are just these little faint specks, and those are more galaxies, right? So we can actually look at distributions, and we can see that to a reasonable approximation, it looks like the universe is kind of uniformly filled with these galaxies. In fact, we end up making the assumption that kind of if you've seen one part of the universe, you've seen it all, because of the way the galaxy distributions just seem to be kind of uniform density everywhere we look. Again, that's a nice spiral galaxy. That's probably that's probably a good representation of what our own Milky Way galaxy looks like. So remarkable photos that we can take now. So this is what the universe looks like in visible light. That's what it looks like in microwave. So the universe is vast. It's kind of an understatement. And so we need some different units of distance. So one of the most important ideas we have to work from is, how do we make distance measurements? How do we know how far things are spread out within the universe? And so we use this unit of light year, and we've seen that before. It's not such a new item for us. But there's another unit that we also make use of, and it's referred to as the astronomical unit. and it's the distance between the Earth and the Sun. So we call these AUs, and 1 AU is 150 million kilometers, or 150 billion meters. It's kind of interesting, I guess, that in astrophysics, astrophysics has kind of their own name for everything. So we'll see more examples of that, but this astronomical unit is always kind of an interesting name for that unit. Like, really? Astronomical unit? Does that tell us anything that it's a length measurement? Anyway, it's a distance from the Earth to the Sun. So for example, how far is it out to Jupiter? Well, it's about 5 AU. So if we're in the solar system, AUs become handy. How far is it out to Pluto? Well, it depends on where it is in its orbit. But you know, typically Pluto is somewhere around 40 AU from us. So how far is it out to the nearest galaxy? And the nearest galaxy is 2 million light years. So from that nearest galaxy, light would take 2 million years in order to get here. Maybe come back a little closer. The nearest star, Proxima Centauri, 4.3 light years. Now, that's kind of in the range where you could use light years, but you could also think about using AU just to get a feel for how they're related. Turns out that 1 light year is equal to about roughly 63,000 astronomical units. So how far is it to the Sun? 1 astronomical unit. How far is it to the next nearest star? 271,000 astronomical units. So to get kind of a perspective for this, what we could do, let's do this. Let's say that we've got a tennis ball here, a Wilson 1. We've got a tennis ball. We could let that be the Sun, right? Now, if the Sun is the size of a tennis ball, how big is the Earth? And it's common to read or hear that the Sun is 100 times bigger than the Earth, or 100 times the diameter is what it actually is. And so, let's see, we've got to find something that's 1/100th the size. I don't know if you guys can see that, but that little crystal or little tiny piece of sand or something, that would be Earth size. Oh, I dropped it. Oh, here it is. Found it. All right. So there's, oh, I dropped it again. So anyway, Earth is this little tiny speck, and the Sun's like this. So you think, well, in terms of diameter, the Sun's 100 times the diameter, but let's think in terms of volume. So if the Sun is 100 times the diameter of the Earth, then in terms of volume, well, that would be, we'd have to cube that, because the diameters would be 100 times as large. To get a volume, we would need to cube the radius, which is proportional to the diameter. So that would be 100 times 100 times 100. That would say that you could fit 100, or not 100, you could fit 1,000,000 Earths easily inside the volume of the Sun. 1,000,000 planets the size of Earth would fit inside the volume of the Sun. So that's really big. Now, if we do this, if we set the Sun at some location, how far away from the Sun would we need to come to be able to get an accurate representation of how far away the Earth is located? And we would have to be able to set that at some location and step back all the way across the room, probably well past here. We don't have enough room in here to demonstrate this. We have to be about 8 or 10 meters away from that tennis ball to represent the size of the Earth's orbit around the Sun. And so now, if we follow that orbit all the way around the Sun, that's how far we travel every year, just with Earth orbiting the Sun. How big is the Moon? And again, let me see if I can track down an Earth and a Moon. So if we say we have an Earth and Moon, and the Earth is a little tiny speck, and the Moon is a speck that's only about 1/4 the diameter, how large is the orbit of the moon? And it turns out the entire orbit of the moon easily fits inside the diameter of the sun. So the moon and its orbit and the Earth, that whole system, that whole double planet system, could fit inside the sun. And how far have people traveled away from the Earth? And they've traveled all the way to the moon. And yet look how far we travel each year as we orbit the sun. So, so that gives you some idea of what some of these distances are like. Now, if this is a tennis ball and it's representing a star, in particular the sun, how far is it to the next tennis ball? And that would be, you know, the nearest star, 271,000 AU. Where would that place us? And you might think, is it on campus here somewhere, or is it maybe you know, somewhere nearby? And it turns out the nearest star using this scale would be out beyond Denver somewhere. So, you know, you got a tennis ball here, you got a tennis ball in Denver, you got a tennis ball maybe in Seattle and Anchorage, Honolulu. That's gives you an idea of how far the separation is between stars, at least in this part of the Milky Way galaxy. So stars are the size of tennis balls, and they're separated by thousands of kilometers. All right, gives you some perspective. Let's move on and take a look. Here is a picture it's not the Milky Way galaxy, it's a different galaxy, but it's a spiral galaxy, and we think it's probably a good representation of what our own Milky Way galaxy would look like. We've got kind of a central bulge, and then we've got this disk. I really like how galaxies look kind of like UFOs, right? Anyway, central bulge, disk, and we have these spiral arms. And what we find is that the spiral arms that you see are involved with local regions of higher density of hydrogen gas, and those are the locations where star formation is taking place. Gravitationally, those clouds of hydrogen are collapsing, forming stars. So that's what actually lights up as the spiral arms, are the locations where the most active star formation is taking place. And so we're most of the way from the center out towards the edge in one of these, not the middle of a spiral arm, off to the side of one of the spiral arms. And the whole package is about 100,000 light years across. It would take 100,000 years for light to get one side of the galaxy to the other. Nearest other galaxy, Andromeda, 2 million light years away. So again, just to give some kind of a perspective as to what these distances are like. So here's some stuff you can read through. 2 million light years to Andromeda. Now when it says it's estimated that there are about 100 billion galaxies, that's observable. So it's saying that if we go back to those pictures that were taken by the photos from the Hubble Space Telescope, we're able to look deep enough into space that there are probably 100 billion or so galaxies observable. But then if you go beyond that, are there just more galaxies everywhere? Is the universe infinite, or is it finite in some sense? Do you reach kind of a limit, or does the universe wrap back around on itself? So we'll talk some more about those possibilities. So here are some more pictures of different shaped galaxies, and we're probably most similar to kind of the one in the middle, kind of a standard spiral arm, spiral galaxy. And then another thing to keep track of is when we look at these objects, we're looking back in time. Now, if I'm looking across the room, light travels about 30 centimeters every nanosecond. That says, 10, 20 nanoseconds maybe, if I'm looking across the room at something. But with these distances, the time delay becomes really significant. Looking at the Andromeda Galaxy is looking at light from the Andromeda Galaxy from 2 million years ago, and that's the nearest large galaxy to us. Looking at some of these other large galaxies, some other galaxies, some of the most distant galaxies that we can observe, that light has been traveling billions of years. So let's get started with distance measurements. How do we know what these distances are really like? How do we know these things are billions of light years away? And we're going to start with some nearby measurements. So there's a series of different techniques we use to measure distances, determining distances in space. And the one that we start with close by for kind of nearby stars is a parallax effect. Now, it turns out that, Earth's orbiting the sun, and that means that Earth, just from standing on Earth, we actually get different views of the star configuration. If I'm looking at all the stars that are out there often, and then if I walk over here, the pattern's going to shift a little bit. In particular, stars that are closer to us are going to shift back and forth relative to the more distant stars. So as we're orbiting the Earth, we can take a series of photos and determine which stars are closest to us and just how far away are they. So we refer to this angle as the parallax angle, and the diagram here shows Earth in January and then Earth in July, and it's got a couple of these parallax angles set up inside here. Now, let's take a look at, and then these pictures right here show, this nearby star is in front of one group of stars at one point in Earth's orbit, and when Earth moves to a different location, that star appears to shift back and forth. Here's another diagram, and maybe this one's going to make it easier for us to come up with the formulas that we want to have. So if we're working in the plane of Earth's orbit, and there is a star, we're trying to determine the distance, and we're going to say the distance here is little d. What we've come up with then is, we can think of it, I guess, as a triangle, but it's a triangle where this base, or this one side of the triangle, is one astronomical unit. It's the distance between the sun and the Earth. So that's one astronomical unit. And then we follow these two lines out to this distant star. Now the distance out to the star is going to be, hundreds of thousands or millions or tens of millions of times one astronomical unit. And that says that these parallax angles are really, really tiny. In fact, if you go back to, thousands of years back to Greek scientists arguing as to whether the Earth is the center of planetary motion or if the sun is the center of planetary motion. There were, astronomers from thousands of years ago arguing that the sun is really at the center of planetary motion in our solar system. But the counter argument was, well, if Earth is in orbit around the sun, then when we look at the stars, they should shift back and forth in their appearance, but we don't see that. There's no parallax. Well, it turns out that there is parallax. It's just that the stars are so far away, it's very, very difficult to be able to pick that up. So to measure these parallax angles, we have to go to much smaller angles than, say, 1 degree. Now, there's a couple of units here. I don't know if you guys are familiar with this, but in angular measurements, radians are kind of the standard, right? So those are our standard units for angular measurements, or radians. But if we're working in terms of degrees, 360 degrees in a circle, a degree gets subdivided into 60 seconds, or 60 minutes, and those minutes of arc get divided into 60 seconds. So in this case, minutes and seconds aren't time measurements, they're angular measurements. So let's try this. Let's take let's say we're looking at the closest star, Proxima Centauri, 4.3 light years away. That was 270,000 AU. And what this triangle is telling us is that the parallax angle that we have, the amount that that star angularly shifts back and forth in our view from one instant in its orbit to 3 months later, is given by, is going to be equal to this distance here divided by the distance out to the star. Now, the distance here is 1 astronomical unit. It's the radius of Earth's orbit. And so what we can do is say that the angle of parallax will be equal to 1 AU divided by the distance out to that star. So let's try that. Let's see what we would expect for that parallax angle. So the formula we're going to be using is this. So we're going to flip this around, not in this example, but in future examples. There's a homework problem or two on this. Distances in AU can be measured by taking 1 AU divided by the parallax angle. Now for this star, we're going to start with the distance and figure out, what are typical parallax angles going to be like? And this is the very closest star to us. So plugging into the formula, that would be 1 AU divided by, the closest star is at 271,000 AU, and it says that would be 3.69 10 to the minus 6 radians. So when we're using this formula, the angle is going to come out in radians. It's an arc length divided by a distance, and that's going to give us natural, well, no units at all, and that means that we're working in terms of radians. So those radians, we could convert those into degrees, 2.11 10 to the minus 4th of a degree, and that worked out to be 0.0127 minutes, 0.761 seconds of arc. So we took that 1 degree, divided it into 60 minutes, took one of those minutes of arc, divided it into 60, and even the closest star is the parallax angle is less than 1 second of arc. So the reason this was not observable because it's a really challenging measurement. So this is a really high level of precision, and I think it wasn't until sometime during the 1800s when the first parallax measurements were made reliably. So yeah, it's a tiny effect, but we have precision instruments. In fact, we've put satellites in orbit that can carry out the most precise parallax measurements. And those can measure distances to stars out well beyond hundreds of light years. So we can get a large collection of stars now that we can accurately measure using the parallax, and that's useful information. Once we have a database of thousands or millions of stars, and we reliably know their distance, we can start asking other questions about those stars. So here's another example. This is an example that was given with this set of slides, which is a little funny. It says that the viewing angle is 89.99994 degrees, which is typically not the way these problems are given. So again, if we bring back Earth's orbit, there's the star that we're trying to measure. They're telling us not the parallax angle, but what they're calling the viewing angle, which is a little funny. Anyway, so it's not the amount that the star shifts back and forth, but it's kind of a complement of that number. So I just switched. I went from there 89.99994 degrees, and took the complement and then converted it into radians. Once I got that angle in radians, I can plug that into my formula. So the distance is 1 AU divided by the parallax angle in radians. That came out to be 955,000 astronomical units. So that's how far it is to the star, at least in astronomical units. If we want to convert from astronomical units back into, say, light years, then we can use our 63,000 AU conversion factor. So I can switch from astronomical units to AU pretty easily, and that gave us a distance of 15.1 light years. So parallax measurements, again, you'll have some homework problems on those, something to be aware of. Now, once we know how far it is to a star, that enables us to determine how luminous that star is. So, for example, I'm looking at these stars and I'm going, wow, that star's brighter than that one. At least viewed from Earth, that star's brighter. Does that mean that it's closer? Or is there anything I can tell from just looking at the stars themselves as far as distance? And no, not necessarily. So we don't really know what the energy output of those stars are until we can do some distance measurements, and now we do. We have a distance technique with parallax. So now that we understand how to do distance measurements, what we can say is this. We can define something called the luminosity of a star. Now, again, I mentioned that in astrophysics there's kind of a different name for everything. Luminosity is power. So in physics, in our physics classes, we've been talking about power and number of watts, and it's a rate at which energy is being generated. And the luminosity of a star, measured in watts, is the rate at which energy comes off that star. So typically we're looking at the luminosity due to the light. There's a bunch of neutrinos coming out because of nuclear reactions taking place in the core. The luminosity typically is referring to the light that's being generated coming off of that star. Now, what they're calling here the apparent brightness. So the brightness of a star, viewed from Earth, the brightness is the intensity. So brightness is what we've been calling intensity. Luminosity is what we've been calling power. So astrophysics has their own name. So the brightness or intensity of light coming from that star is equal to its luminosity, or its total power, divided by, now it's 4 pi d squared, and that's because the light's spreading out uniformly in all directions. If we're observing that light, so here is the star, it's got a certain luminosity to it. That's what we're looking at here, the luminosity or power. That's getting measured in watts. And that luminosity is heading out in all directions. And here are the two formulas side by side. So we've looked at these diagrams. It's our very common diagram of a central energy source sending energy spreading out from a central source, and that the intensity of that then drops off like distance squared, and the 4 pi d squared is the surface area of that spherical shell. Now, what we're saying is that, for 43 chapters, we've been defining intensity and power and distance using these symbols, and now the power is getting replaced by luminosity, and the intensity is getting replaced by brightness. So just be ready to use either set of symbols. It's easy enough to kind of slip back and forth, I guess. Write those side by side in your notes and remind yourself what brightness and luminosity are referring to. So intensity measurements or brightness measurements are going to be in watts per square meter. Now let's talk a little bit about what does determine the luminosity of a star. What's going to determine how much energy, or the rate at which energy is being produced inside a star, and it's going to depend on the rate of nuclear fusion. So back in the previous chapter, chapter 42, we looked at nuclear fusion. In fact, we looked at some of the nuclear fusion reactions going on inside stars. And what we said is most stars, 90% of stars or more, are undergoing hydrogen to helium fusion, but that some stars, in the later cycles of fusion, all stars start out with hydrogen to helium fusion. So when stars first form, gravitational collapse of a bunch of hydrogen clouds. The core becomes a really high temperature from that gravitational collapse. Nuclear fusion kicks in, and the first process is hydrogen to helium fusion, because hey, that's what the star is made out of, basically, is a bunch of hydrogen. And then that hydrogen is converting into helium. In later stages of stars' development, some stars, not all, the heavier stars, are able to generate heavier elements by fusing helium into things like carbon and oxygen. Those can be additionally fused into, well, I put some representative elements here, heavier elements like silicon or calcium, and then finally iron. And then back in chapter 42, we said once you get to iron, you can have fusion reactions beyond iron, but they're not going to release energy anymore. That's the end of the energy production. Generating elements that are heavier than iron actually require energy. So the Q values are no longer positive for those reactions. So here's a star, and it's always important to remember, hey, it's not like nuclear fusion's happening throughout the star. Nuclear fusion requires temperatures in the extremely high pressures and temperatures in the tens of millions of Kelvin. And the surface is nowhere near those temperatures. Surfaces are in the thousands of kelvins. The cores of stars are in the tens of millions of kelvins. And so it's really just in these core regions where these fusion reactions are happening. Now, if a star is going to be more luminous, that means it has to run fusion reactions at a faster rate. And the general trend is if it's a bigger star, now by bigger here, I guess we say a star with more mass. So when stars form, what is it that kind of separates one star from another? They're all basically made out of the same stuff. Some mixture of, predominantly hydrogen with some helium thrown in, left over from earlier phases of the universe. If you start with a lot more material, you just, some stars are bigger than others. Just by chance, the gravitational collapse process that takes place ends up with some collapsed clouds of hydrogen aren't as big as other collapsed clouds of hydrogen. And the ones that are more mass, well, that's more gravitational force and more gravitational potential energy. The core rises to higher temperatures and pressures, and that boosts the fusion rate. So we end up with a higher fusion rate, and we end up with higher luminosity. Bottom line, higher mass stars generate energy at a faster rate. Now, the flip side of that, you might ask, is, well, what about how long they live then? Because if you've got these stars that have 10 or 100 times more mass than some other star, sure, they're going to be more luminous, but are they going to run through their fuel so fast that they have shorter lifetimes? Or is that extra fuel going to make them stay around for a long time? And it turns out that the highest mass stars, as the mass of stars increases, the luminosity goes up very rapidly and the lifetime goes down. So the lowest mass stars run fusion at a lower rate. There's plenty of time for the hydrogen to cycle through the core, so much of the hydrogen ends up undergoing nuclear fusion. The highest mass stars, the fusion rates are much faster, but there's not time for thorough mixing, so a lot of the hydrogen never even undergoes fusion. And then they have much shorter lifetimes. Okay. All right, so that's kind of the story of, why are some stars more luminous? Well, it's basically because they start out with more mass. And then what determines how bright a star is viewed from Earth, and then it's the luminosity divided by 4 pi times the distance squared. All right, so here's a problem that they've given us. They've said that we have a particular star. It's got a certain luminosity. It's 10 light years away from Earth. And they want to ask about what its brightness will be like. So I set it up this way. I set it up taking a look, setting up some of these numbers. I did put some numbers in here. So I've got the 10 light years in here. So at 10 light years, that's 9.46, 10 to the 16 meters. I've got my two brightness formulas, my brightness and then the formula written in terms of intensity and power. Here is the star, here is Earth. And let's say that this, I made up a luminosity, so I added this in. Let's say that the star has the same luminosity as the sun. Maybe actually the problem did say that. So here's the luminosity. I put it as the same luminosity as the sun. The sun's luminosity is 4 times 10 to the 26th watts. And that says that if it's 10 light years away, that the brightness would be given by, well, there's the luminosity divided by 4 pi distance squared. And it says when I look at that star, which is 10 light years away, and that's not very far, right? The closest stars are like 4.5 light years away. So 10, that's still kind of in our neighborhood. But that star is going to have a brightness, 3.56, 10 to the minus 9 watts per square meter. Now it could actually be a pretty bright star in our sky, but it's like a 10 to the minus 9th watts per square meter. That's kind of the intensity of a bright star. Now let's compare that with the sun. So I ran this star that's out 10 light years away. Now here's an identical star, the sun, but this one is only 150 billion meters away. So you can tell it's a big difference. This is 10 to the 11th versus 10 to the 17th roughly. The brightness here then, it's the very same formula, I can apply this to the sun. The brightness here is going to be 1400 watts per square meter. And now if I take the brightness of the star that I calculated versus the brightness of the sun, what I'm finding is that the sun is 400 billion times brighter than that star, just looking at the brightness. Now this problem can be done in ratios, and it's very common in astrophysics, well, throughout physics. But astrophysicists a lot of times are just kind of doing comparisons. Sometimes they don't know all the information about something. Sometimes some of the information is missing. And so they can work in terms of ratios to make these kind of comparisons. So let's try a ratio approach. What we could do is this. Let's say that the brightness of these two stars, brightness of the sun, brightness of this other star, that's 10 light years away. Well, I could write a ratio of brightnesses, and then I could put in a ratio of this rest of the formula. The luminosities divided by 4 pi distance squared. So here's the rest of the formula for brightness for star number 2 and star number 1. And then we'll be doing ratios, of course, as we look for things that cancel out. And the 4 pi's go away. And then we look for other ratios that come out of that calculation. So I'm getting L2 over L1. I'll write that down as a ratio of luminosities. And then I've got d squareds, but they're in the denominators. So the thing you have to be aware of with ratios is don't get it backwards, right? You got to get the ratio set up the correct way. Don't get the inverse. So it looks like the d1 is going to come up top and the d2 will be in the denominator. So I'm getting d1 over d2 squared. Now in this problem, what we're assuming is that the two stars have the very same luminosity. So I got to take the L2 over L1 and just write that as a ratio of 1, since the luminosities matched. Now it was the distances that were different. So what it's saying is that the ratio, or the comparative brightness between the two, is going to depend on the distance ratio squared. And that star at 10 light years turns out to be 631,000 times farther away than the sun. And so at 631,000 times farther away, we square that, and that also gives us this number of 400 billion. So yeah, the sun's going to be 400 billion times brighter than this close star, relatively close star, because it's so much closer to us. Now another property that we want to be able to take a look at with these stars is surface temperature. So let's see where we are in terms of properties of these stars. We used parallax to get a distance. Once we knew the distances, we could look and see how bright the stars are viewed from Earth. We could look at the starlight intensity. That, along with distance, enabled us to determine luminosity, which was an intrinsic property of the star itself. So now that we know the energy output of those stars, another property we could make a comparison with is surface temperature. So this is telling us that surface temperature varies between about 3,500 Kelvin all the way up to about 50,000 Kelvin. So here's a nice diagram. When we look at stars, surface temperatures run, as this was saying, from about 3,000 Kelvin up to about 50,000 Kelvin. And because of the temperature, again, think back to chapter 37 and the Planck radiation distribution function. What we're seeing is that at lower temperature, most of the light actually is coming out as infrared. At 3,000 Kelvin, most of the luminosity of that star is going to be in the infrared. What is in the visible part of the spectrum is going to be mostly in the red part of the spectrum. So that's a red star, and we'll see what types of red stars we have. And then here's a little higher surface temperature, and a little higher and a little higher. The sun surface temperature is about 5,800 Kelvin. So the sun's appearance is, in here somewhere, I guess more like this. And then as we go to higher and higher temperatures, we go from kind of yellow to yellow-white to white, and then at the highest temperatures, some of these stars, most of their energy is coming out as ultraviolet. And so the portion that we can actually still see in the visible is in the blue or the violet part of the spectrum. So that's kind of our spectrum of star colors. So what we want to do is determine what the surface temperature of a star is. It's probably useful information, and we have a method, going back to formulas from chapter 37. We can look at the peak wavelengths for different stars and determine what their surface temperatures are. Now, in addition to that, and probably even more important, is that when you're looking at specific lines within the spectrum of light, different elements, hydrogen, helium, different lines for different elements are more prominent at different temperatures. Has to do with which quantum states the electrons are shifting around in. And so that's another determination, just kind of the peak wavelength along with these kind of properties in the spectrum. So here's a problem. It says that we've got two stars, star A, star B, and one of these is a reddish star, and it has a peak wavelength at 700 nanometers, and then we have another star that's bluish, and it's got a peak wavelength at 350. So that's off into the ultraviolet. And then the peak wavelength here is just kind of at the far red end of the spectrum. So let's see what kind of properties for these stars we can come up with. So here they are, star A, star B. These are the numbers that they gave us. So that's the given information. 700 nanometers for a peak wavelength, 350 nanometers for peak wavelength. And then we look back into chapter 37 and we go, oh yeah, we did this with the Planck radiation distribution function. Peak wavelength times temperature is this constant value of 2.90. So I can turn that around and solve for the temperature in terms of the peak wavelength, and I've used that formula in this example to determine that for star A, surface temperature is around 4,000 Kelvin. Came in at 4140 kelvins. And then for star B, this came in at 8280 Kelvin. So I guess that makes sense. This wavelength was 1/2 as long as this, and so if I shorten the wavelength by a factor of 2, that must mean that the temperature is higher by a factor of 2. So I've got these two stars at these two different temperatures. Now another relationship that we can come up with, and I think that was included in that problem. The other question they ask about is, okay, fine, we know what the surface temperatures are. What about the diameters of the star? Is there a way we could actually figure what the diameter of a star is? Now, that seems unlikely, I guess, but it turns out we can. We can actually get measurements of diameters of stars. The stars are so far away, we certainly can't look through a telescope and do a measurement of their diameters. Most stars that we look at are so far away, they don't appear as disks. There's a kind of a point of light. But let's do this. Let's assume, so I went in and put some numbers into this also. Let's assume that both stars are really luminous. So let's assume both stars are 25 times the luminosity of the sun. So their power output is 25 times as much. And what that gives us is a value for their luminosity, 1.0, 10 to the 28 watts. So again, I've got the luminosity or the power output of the sun listed, and then the power output for these particular stars. Now, here's a relationship that we can write down. Now, we already talked about luminosity, and we said that what determines the luminosity of the star is how rapid the fusion reactions are taking place, and that's typically related to the mass of the star and how long the star has been shining. How much fuel has it run through, what's the current makeup of the materials in the core of the star. But here's a relationship that we can use. This is not determining the luminosity, but what this is saying is that the power, the rate at which energy is coming off something in light, depends on a surface intensity times a surface area. And that also is something that we saw, I think, in chapter 37. And then the first time we saw it was back in thermodynamics, back in probably chapter 18 or 19 maybe. So we've seen this a few times. This was our Stefan Boltzmann constant times temperature to the fourth. And what that told us was the intensity of light coming off the surface of an object at a particular temperature. Well, it turns out that the way stars are generating these photons, the photons are generated and then they're absorbed and they're new photons, and so kind of down in the mixture of material inside a star, it's a good representation of an equilibrium material. It's an equilibrium distribution of light that's being generated. And then the light that we see coming off the star is kind of the light that leaked out. The light was generated down inside this mix of high temperature gas, and then some of that light is leaking out. And so we can use that. We can use the sigma temperature to the fourth. Now the total surface area for a star, we'll say it's spherical, that's 4 pi times the radius squared. So there you go. There's a way that we can relate the surface area, or the radius or diameter of a star, to its surface temperature and its luminosity. And it turns out that, well, a few slides back we saw we can determine luminosity. Once we know how far it is to a star, we can measure how bright it is from Earth and determine the star's luminosity. And then the surface temperature can be figured out looking at the spectrum of light coming from the star. So we can use that formula right there. So let's go back over to the calculations that we've got. Now I've made an assumption that the star has this much luminosity. We've determined that. And so what that says is, well, coming back to the intensity formula, sigma times temperature to the fourth power, that says I can take this temperature to the fourth power, multiplied by the Stefan Boltzmann. That says the surface intensity for this is 16.7 megawatts per square meter. So every square meter of surface area on that star, 16.7 megawatts of light coming off that surface. That's a lot. But if we just double the temperature, remember temperature is to the fourth power in this formula. If we just double the temperature, that's going to give us 16 times the intensity. So this higher temperature star, light's coming off that at 266.5 megawatts per square meter. So that's a factor of 16 if I'm thinking ratios. Now, what about the surface areas for these? Well, what we assumed was that the red star and the blue star, just by chance, happen to have the same luminosity. Is that a possibility? And we'll see that it is. They're probably at different stages in their development, in their evolution. But assuming that they both have this luminosity, we end up with very different diameters. So it's saying this, is there a way that a red star at a lower temperature could be actually at the same luminosity as a blue star at a much higher surface temperature? And what it's saying is that, sure, it could be that both stars have kind of similar luminosities, but one star is just more spread out. So let's say I got a star, two stars of the same luminosity. For whatever reason, one star is fairly compact. That's going to make that a blue star. But if the other star happens to have material more spread out, even though it's generating energy at the same rate, the surface of that star is going to be red. So that could be the difference. So let's see how this works. And so if we sample a bunch of stars, we talked about getting distance measurements and luminosity measurements and building up a database of data on, thousands or hundreds of thousands or millions of stars. When we do that, what we can do is we can plot them. And one common way to plot the properties, not the location, but the properties, is using what's called an HR diagram. And the HR diagrams have luminosity on the vertical axis. So as you start here and work your way through the diagram vertically, what you're looking at are more and more luminous stars, stars of higher and higher luminosity. Now the horizontal axis is in terms of surface temperature, and I'm always suspect on, see, they never scale them the right way. So on the vertical axis, it is a logarithmic scale. If you look here, this is in watts, but it's going 10 to the 23rd, 10 to the 24th, so it's logarithmic in that each equal increment is going up a factor of 10. It's not equal increase, but it's factor of 10 increases. And then along the horizontal axis, I don't know how to interpret this, 3,500, 5. So this is probably got a little bit of logarithm anyway. Always watch the way the axes are labeled. Now here, this is surface temperature. And what Hertzsprung and Russell did is they got it backwards, right? They should have started with temperature here and had increasing temperature in that direction. I always feel like, hey, if you guys turned in a lab report and you mislabeled one of the axes and started with high temperature here and low temperature here, you get points marked off, right? You would lose points for that. But Hertzsprung and Russell chose to have the higher surface temperatures to the left, lower surface temperatures to the right. And so when we do classify, we get our database of star data, and here's this star's luminosity, and here is its surface temperature, and we start plotting that, we end up with a particular pattern. We end up with the majority of stars, 90% or more of the stars, follow a pattern of correlation between surface temperature and luminosity. And by that, what we're saying is, if you're at a low surface temperature, you have low luminosity. If you're at a high surface temperature, you have high luminosity. So those two properties are correlated for most stars. But notice there's also some exceptions over here, this region that's labeled as red giants, and there's some exceptions over here, this region labeled as white dwarfs. But for now, let's just talk a little bit about this general pattern that we see down the middle that's called the main sequence. And I always feel like main sequence, that would be a great name for a rock band, right? It could be the main sequence. Anyway, let's see. The main sequence turns out to be stars that are in the process of fusing hydrogen to helium. It's the earliest stages in a star's development or a star's evolution. That first step in fusion is hydrogen to helium. And what happens is the stars with low mass are low luminosity and low surface temperature. And then as we move through the main sequence, if we do mass measurements of these stars, we find that the masses are steadily increasing as we move along the main sequence. So these are the very lowest mass stars, these are the medium mass stars, and these are the highest mass stars. And so for stars that are in the first stage of development, fusing hydrogen to helium in their core, they end up being classified on the main sequence, and the higher mass stars are going to have the high luminosities and the high surface temperatures. Now, at these surface temperatures of 10,000 Kelvin, so these stars are going to be blue. So I'm starting over here at 3,500 Kelvin. These stars are going to be red surface area, and then the orange, yellow, white, blue as we go through the main sequence. And you can see the sun is right here. It's at about 4 times 10 to the 26th watts in terms of luminosity. It's got a surface temperature of about 5,800 kelvins. And so there it is on the main sequence, placed at that location. Now, in the example we just looked at, we said that we had 2 stars and a red star and a blue star. And let's see, one was at 4,000 Kelvin, and that star at 4,000 Kelvin, they had luminosities of 10 to the 28th watts. So one of those, in the previous problem, one of those examples we looked at falls into the classification of a red giant. So that's one of the kind of off the main sequence exceptions. And then the other star we looked at was 8,000 Kelvin, and that came up, and here we are at 10 to the 28th. So it's like these 2 stars. So the stars that we were looking at, now that one would be blue, red surface, and it would be very spread out. This one is blue on the surface and much more compact. Okay. So I think we'll stop there. It's probably a good time to take a break. We'll come back, talk more about this diagram.